Hello, in this video we're going to look at why we can assume the population variances are 1 when we're calculating sample sizes for means or mean vectors. And this is when the variances are known and unknown. And the reason that it works this way is because when we think about sample size, we think of it in terms of an effect size. So the difference in the means, or what shift in the means do we want to detect, divided by the standard deviation. So the shifts are in terms of standard deviations. And as long as we think about sample size like that, without loss of generality, we can assume the population variances are 1. And that's what we want to show in this case. So the first 2 pages are like a univariate case, and pages 3 and 4 are the multivariate case. And in both cases, we can assume without loss of generality that the population variances are 1. So to set this problem up, we want to test the hypothesis that the mean is equal to mu naught, or is it greater than mu naught? Okay. We're going to assume that our data follows a normal distribution with some mean and some variance. For this case, we're going to assume that sigma squared is known. And then we'll look at when sigma squared is not known. So the test statistic is x bar. It's the mean, right? So if the sample mean is much bigger than mu naught, then we'll say, well, the evidence says that we should reject and conclude that the true mean is definitely bigger than mu naught. If it's not much bigger than that, or similar to mu naught, then we'll say, well, there's not enough evidence to reject, and we have to accept the null. So what we do is we have to know what the distribution of our test statistic is under different scenarios. So we say under h naught, so that means we assume that mu is equal to 0, and then we find the distribution of our test statistic. Well, the sample mean is a linear combination of normal random variables, so itself is a normal random variable. So the distribution of x bar is normal with mu naught, right? Because we're under the null, and the variance is sigma squared over n. Now to find the critical region, we want to find the probability, assuming h naught's true, that when x is greater than some c, that probability is alpha. So that means when the null hypothesis is true, that we don't reject it very often, only maybe alpha % of the time. And to draw a picture, here's our normal distribution with mean mu naught, right? We're assuming that it's true. And there's some c out here that the tell area is alpha. And then what we do is we want to find what that c is. And then there's a relationship between any normal distribution and the standard normal that we can map c down into its equivalent standard normal. So we want to find z sub alpha that makes this tell area alpha. And the formula is that this z is the original c minus the mean divided by the standard deviation. And that's it. Now we can back solve for c, and that's what it is. This is the c. So if our test statistic is bigger than this value, we reject the null hypothesis. And that's it. That's how we conduct the hypothesis test. But when you're calculating sample size, you have to assume that the alternative is true. So you say under h1, that means that in reality the mean is really bigger than mu naught. And the test statistic is the same, but we have to find the distribution of our test statistic under h1. And so remember, we're calculating sample size, so we want to be able to detect some sort of shift in the mean. So we have to assume that the true mean is mu1, which is in the alternative region. But that says, so the distribution of our test statistic x bar is normal mu1 and then variance sigma squared over n. And then this is where mu1 is bigger than mu naught. It has to be because we're assuming that we're under h1, which means that we're bigger than that, the mu naught. So the power it's the probability, assuming that h1 is true, that we reject the null hypothesis when we should. So that means the probability that X bar is greater than C, assuming that H1 is true. And oh, my cat wants outside. So this probability is, since it's normal, we can subtract the mean and divide it by the standard deviation, and then it becomes, we're in the standard normal case. And then what I do is I multiply this up. So when you divide by a fraction, you invert and multiply. That's what this is. Now the C we determined was this, so I plug that in, and then minus mu1, right? Now we multiply this in, and we get this right here. And so this is power. And so what you do is you pick some in, and then you calculate this probability, right? Which is straightforward. We know Z alpha, that's, and mu naught is, in the null, so we know it. We picked mu1, so we know, and we know sigma. So n is the only variable. So as we increase n, this power goes up, and then we just keep increasing n until we achieve the power we want, and that's how we calculate sample size. Now, if we think about this mean difference here as some sort of multiple of a standard deviation, like this, so it's a standard deviation shift. So maybe we want to detect a half of a standard deviation shift in the means. So we can think about it like this. So it's minus k sigma. So it's k standard deviation shifts, and it's minus because mu1 is bigger than mu naught, right? Now, if we think about it like this, then when we plug this in for the difference of the means, the sigmas cancel, right? And we're left with this. This is how we calculate power. So if you go in saying, hey, I want to detect this a 1/2 standard deviation shift in the means, you just put 1/2 here and then increase in until it achieves the power we want. This is the same as this. So now let's redo the problem, but instead of assuming that our data is normally mu and sigma, let's assume it's mu and 1. So the variance is 1. And let's assume we want to detect a k standard deviation shift in the mean. So the same exact problem here. So and we'll go through this a little quicker, but the problem is set up 100% the same. So the mu is equal to mu naught, or is it greater than mu naught? We assume that our data are normal with mean mu and variance 1. Now, our test statistic is still the same. So under H1, the distribution of mu naught is normal, mu naught, and 1 over n, right? But when it was sigma, then it was sigma squared, over n. But since the variance is 1, it's 1 over n. So the critical region is the same. So the probability under the null hypothesis, the probability that we reject the null, which is X bar greater than some constant, we want that to be alpha. That implies, in going through the same calculations before, that we get this. C is equal to this. And the only difference before that this was a sigma. Now, under the alternative hypothesis, we want to find power, the probability that we reject, assuming the alternative is true. Then we subtract the mean, divide by the standard deviation, and we get this. So now we invert and multiply. That's what this is. We replace what C is, and of course we have minus mu1. We multiply that in, we get this. Now, if we think of this mean shift, the difference of the means, as in of k standard deviations, we can just put that in. So k times the standard deviation, but the standard deviation is 1. So we just put k here. Now we increase in 1, 2, 3, 4 until this power becomes high enough, and we're done. But this is 100% identical to what we did before, right? This line is 100% the same as the previous one, whether we thought of as the variance as sigma squared or just thought of it as 1. And so that's the reason why, without loss of generality, we can say that the population variances are 1. Now let's look at the multivariate case. So these are mean vectors, right? Is the mean mu1 or mu naught, or is it not mu naught? And again, this is a p, there's p components into that vector. So our data follows a multivariate normal, p dimensions, some mean vector, and some covariance matrix, right? And let's assume we don't know it. So it's an unknown. And we have a sample size from 1 to n. Our test statistic is the Hotellen's t-squared. So n times, the sample mean, which is, this is a vector, and that's a vector, right? And this is the sample estimate of the covariance matrix. So, some might call that S, and then the difference. And so this is it. That's a standard Hotellen's t-squared. And now under H naught, so when the H naught is true, so the mean vector is mu naught, the distribution of our Hotellen's t-squared is this. So the t-squared, our test statistic, is distributed as a multiple of a central F distribution, where p numerator degrees of freedom and n minus p denominator degrees of freedom. The critical region that we want to find some C, such that when our test, the probability of the test statistic being greater than it is alpha, and this is again when the null hypothesis is true, which means we don't want to reject it very often when the null is true. Now, you can show that this C is this, okay, so it's the same p n minus 1, n minus p out front, but this is a quantile for a central F distribution. We're at the p numerator degrees of freedom, n minus p denominator degrees of freedom, and alpha is the significance level, right? And with a picture, it would look like this. So if this is the central, F distribution times a constant, this under this curve there would be alpha, and if our test statistic is in here, we would reject. Anyway, that's how you do this test, okay? So under the alternative hypothesis, the distribution of our test statistic is this. So it's t-squared, our Hotellen's t-squared, is actually a multiple of a non-central F distribution, right? So p numerator degrees of freedom, n minus p denominator degrees of freedom, and lambda is the non-centrality parameter. And the non-centrality parameter is this. So it's n times, and remember, we're under the alternative hypothesis. So normally this would be x bar, but we're assuming that it follows a normal multivariate normal with mean mu1. So we put mu1 here minus the null mean, the true population variance, mu1 and mu naught. And so this is a non-centrality parameter. So even though we didn't know sigma, it actually shows up in the non-centrality parameter. And so when we're doing power calculations, so power is actually the probability that we reject a null hypothesis when we should. So we're assuming that the alternative is true, then this is power. And so what you do in this distribution, the n is in the denominator degrees of freedom and this non-centrality parameter. And so if you look at this non-centrality parameter, this is a constant. We pick the value, the mean vector in the alternative region, so it's a constant. The population covariance matrix is a constant. So n is the only non-constant. So you pick an n, and find this probability. If it's not high enough, then you increase n until it achieves the power we want. And it's kind of a neat little thing that the non-centrality parameter, the larger it gets, meaning you increase n, the more that this non-central F distribution is shifted to the right over this the rejection region or critical region. Well, anyway, that's how you calculate power. You have to come up with these estimates. But if we think about this shift in the mean vector as each component is a shift in standard deviations. So this mean vector, which is here, the first component is going to be some multiple of the standard deviation for that component. The second component is going to be some multiple of the standard deviation for that component. And it's actually going to be this case for all p components. We're talking in terms of standard deviation shifts. So this vector can be thought of as this, where this is a diagonal with the standard deviations down it. And the k's are the multiples of the standard deviation shifts that we want to detect. So we can think of this as v times k, where k is a vector. Now, let's examine the noncentrality parameter in a little deeper. So this is it. So this is a noncentrality parameter from the previous page. But any covariance matrix can be broken down into V rho, where this is the correlation matrix V. And V, remember V was the diagonal of the standard deviations. This multiplied together, you get the covariance matrix back. And we're thinking about the shift in the means as multiples of the standard deviations, right? So we can put that in there. Well, when we multiply that -1 through, we get this, and we put the transpose through, and that's diagonal, so it's symmetric. And then the V's cancel, and we're left with this. So it's in this K vector, which are multiples of the standard deviation shifts we want to detect. And then this is the correlation matrix. So it's variance, the variances are 1, or not the variances in this case, but the correlations are 1 and K. So now let's redo the problem, and we think of, instead of saying that our data follows a multivariate normal with some mean vector and sigma, let's assume that the variances are 1, which makes it some sort of correlation matrix, right? So let's assume we want to detect Ki standard deviation shifts in the mean. So let's redo the problem. So it's 100% set up the same way, except we're going to assume the variances are 1. So is the mean vector mu naught, or is it not mu naught? The test statistic is the same standard Hoteling's t squared, but right here, so the sample estimate of this is calculated the same way as the sample estimate of the previous setup. So under the null, this is distributed as some multiple of an F distribution, actually the same one, numerator P degrees of freedom, denominator n minus p degrees of freedom. The critical region is set up like this, so we have to find the C that makes this true. Remember, we're under the null, and that's this. So where this is the quantile of a central F distribution. And this is actually the same C as the previous setup, and so far the only difference is we're assuming the variances are 1. Now under the alternative hypothesis, the distribution of our test statistic follows a multiple of a non-central F distribution. So this is the same multiple, and this is a non-central F, but the non-centrality parameter is a little bit different. So lambda 1 is n times the difference in the mean vectors, the inverse of our covariance matrix that we're assuming is true, right? Difference in the mean vectors. But if we think about this as a multiple of our standard deviations, it's actually just K, because the standard deviations are all 1. So we end up with this. And so this is the non-centrality parameter. But this was the identical non-centrality parameter as the first test. So calculating sample size under the first scenario is 100% the same as calculating them when we assumed that the variances were 1. And note that when P is equal to 1, so it's a univariate case, this is the univariate t-test. So if we're going to find sample size in the t-test setting, we also assume without loss of generality that the population variance is 1, and we just want to detect a certain standard deviation shift in our mean vectors. So without loss of generality, we can assume the population variances are equal to 1 when we're calculating sample size. And that's the justification for it. Well, that ran a little long, but I hope you enjoyed that, because I sure did. It's good information. And like the video and subscribe so you don't miss the next one. Thanks. Bye.